Clayton Spinner here. This is my submission for the ATTiny project. This is the first one without interrupts, just the temperature sensor. Most of this code is from Professor Rosine, but again, we had to write our own conversion, so that's this down here. First thing I'm going to talk about is this up here. How many samples of the input signal do we get? If each single cycle instruction takes 1 microsecond, you need to count the following instructions. So what I do here is state 1 counts the number of ones, state 2 counts the number of zeros. I just counted up the amount of time each state takes to go through, or rather the number of cycles. And the way you do that is you take a look at the data sheet on the ATTiny, and you go to the individual instructions. You find each one. First one is add immediate to word. You come over here, you look, and you see it has 2 cycles. Put it there, and you just go through each one. Most of these are 1. The branches are either 1 or 2, depending on if they branch or not. So, for instance, branch not equal to 0, it will, every time it branches, it takes 2 cycles, and when it doesn't branch, it takes 1 cycle. So temp is set to 10. It decrements temp each time, and once it decrements temp below 0, or 2 equals 0, the 10th time it will continue through. So this will go through 9 times using 4 cycles each, 1 for the no-op, 1 for the decrement, 2 for the branch, and then the last time it'll just do 3. So you add up the rest of these. This last branch is 2 every time. It always branches back to WH1, basically while 1 or while 10. The very, very last time it'll do 1 cycle, but we're not going to worry about that difference because it only does it once. It's only off by 1. State 2 does the basically exact same thing, only it's counting zeros, but it has the same number of cycles. And so the way you find out the number of times it's going to count ones and zeros is you take a look at the temperature documentation. It gives us that T1 is nominally 10 milliseconds. So that's under normal conditions, most temperatures. It'll be putting out ones for 10 milliseconds at a time. And T2, which is the number of times, or the amount of time it puts out zeros, is based off this equation here, based off the temp. And if you take the temperature, which was basically 20 degrees Celsius, give or take a couple degrees, that gives you the value 9.3 milliseconds for T2. So then you take those two values and divide them by each by the number of microseconds the block takes, and that gives you the number of times this will execute, and add 1 to the ones or add 1 to the zeros respectively. And those two numbers are, excuse me, for the ones, 212 times about, and 197 times for the zeros. So those numbers are only in the hundreds. They're pretty low, and it's mostly because of these two blocks here, which just take up a lot of time doing no ops and just repeating through just to count. Basically slows down the number of times it goes through the loops to count up, so we don't have ridiculously large numbers in X and Y. Next I'm going to go through, just start going through the top here. Here are the variable allocations. It basically is just giving names to individual registers. Now these are not setting up new variables in memory like in normal languages. This is just in assembly, it's just giving names, giving more recognizable names to the registers that are already there. So temp is going to refer to R16. You could use R16 in the code, but then you might get lost, forget what it is if you're using it R18, 19, 20 altogether. So that's why we give them recognizable names. This area here sets up the outputs and also where it's going to be receiving info from the temperature sensor. You load immediate into mask ones. This is for the tens places, the tens place LEDs. It's on port B that it's put out to, and basically you send the mask out here. The ones, effectively ones turn the LEDs off, zeros turn them on. So sending ones to the lowest 3 bits turns the LEDs off. Make sure they're set to off at the beginning of the program. Same thing here, out to port D. The LEDs for the ones place are on bits 2 through 5, and so that's why we have here we just set mask just everything to 1 and just put it out to D. That turns all of these LEDs off. And then lastly for port B, we give it one here to tell us that on bit 3, that's where the information is going to be coming in from the temperature sensor. That's where the temperature sensor is hooked up. So it's basically going to be listening for info there. Next we get to state 0, and this is just to wait. We don't want to start counting our 1s or our 0s in the middle of the temperature sensor's run, like in between 1s and 0s, so like we only get half of the 1s or half of the 0s, say. So this just waits until we start seeing 1s for the first time, and then we'll start counting the 1s. And it does that by, actually, I'm sorry, first it actually initializes X and Y to start off with. It puts 1 into X and 1 into Y. Now this 25 is here. I'll explain this in a little bit. This is hex for 25. It does put 25 into here, and that has to do with the conversion later on. It actually does part of the conversion here while it's counting, but I'll get more into detail about that a little bit later. So right here, it puts the value of the pin into temp, and this pin is getting information from the temperature sensor. Set mask equal to what the temperature sensor would be if it was getting a 0. You compare them with the and if they're equal, you just branch back here. So basically what that does is it keeps branching while the temperature sensor is spitting out 0s, and then once it starts putting out 1s, it jumps down to state 1 and starts counting. So I basically already went through state 1 and state 2. State 1, every time it counts, it adds 25 to X. State 2, every time it counts, it adds 1 to Y. They'll go through that a couple hundred times, and then after it breaks out of those loops, it starts the calculating to put the temperature out to the LEDs. Now what's interesting is the way you calculate the temperature is shown here with this equation. Let me get this on the screen. Temperature equals 235 minus 400 times T1, which is the 1s, divided by T2, which is the 0s. Now, instead of doing 400 times this number divided by this number, we want to try to avoid using large numbers, especially if we were to be counting. If we weren't to have like these no-ops here, we'd be counting a lot larger numbers, and we don't want to have an overflow error or anything like that. So to rearrange this, you can actually take the equation, split the 400 up into 25 times 16, which just equals 400 again, and then move the 16 from the numerator into the denominator, and it effectively does y divided by 16. So then you only have to do 25 times x and y divided by 16, which is a little more manageable than x times 400, which could potentially give us too large a number. The y divided by 16 can be accomplished pretty easily by a logical shift right, and that's what happens here 4 times. ROR, R-O-R, is a shift right, but it rolls over into the carry bit, and we do that because the Y register is split up into these two, the high bits and the low bits. Oh, I just moved that. And we want to carry over the high bit in the least significant bit in the high bit to the most significant bit in the low register, so that way we don't lose that bit. And then we reset it each time, because if we say carry over the lowest bit in the low register, we don't care about that. That's just lost to the division anyway. So we shift right 4 times, which 2 to the 4th is 16. And so it's basically y divided by 16. And then all we have left to do is the 235 minus x divided by y. And now this is where that 25 comes in. You have to multiply x by 25, and we actually already did that in state 1. Every time we add 1 to x, we don't add 1, we add 25, and that effectively does the multiplication there, rather than doing adding up all the 1s and then multiplying by 25. We just add 25 each time, and it gets that set up for us. So lastly here, this does the subtraction and the division at the same time, and it does that by adding y to z and then comparing z to x to see if it's equal to it, or still lower than it, rather, with this branch on low up here. And then it decrements TMPC 1 time, which has 235, and it keeps adding y into z over and over again until z is equal to x. And that effectively does, it will decrement that number of times, which is the number of times that y goes into x. And that's basically x divided by y. So that will give us 235 minus x divided by y. So that's kind of a clever way to, do those at the same time. Then basically we have this conversion now. Now this is the part that we were asked to write. So I'm going to go through this. I put 10 into 10, just holds the value 10. This is for binary decimal conversion, which puts out, it will put out on the LEDs, one set of LEDs will hold the 10's value, one set will hold the 1's value. So what I have here is I throw TMPC, which is now our temperature, into the variable temp. I just reuse temp. 10's will hold the number of 10's we have, right? So I set it to 0 to start off with. 10 is what I'm going to be decrementing from temp, or subtracting from temp rather. Basically the way this works is it's temp minus 10. If it hit a negative number from this subtraction, it jumps over to the 1's, which basically means it's already taken the number of 10's out that it possibly can. If not, it increments 10's by 1, meaning I had added one more 10's to it, and then jumps back up to convert 10's. So if the temperature is, say, 56, it'll subtract 10 from 56, it'll be 46. It won't branch. Increment the 10's by 1, jump back up here, subtract 10, you're down to 36, won't branch, increment the 1's. It'll do that 5 times until it gets to the value 6, and then when it subtracts 10 from 6, it'll hit a negative number, so you'll have the branch on carry. You'll have the carry bit will be set, and it'll jump down to the 1's and start doing that. Then this 10's will have been incremented 5 times, and then you'll have 5, which is the 10's place for that number, which is what we want. Start 1's does the same thing. I add 10 here because this last subtraction put it into the negatives. We don't want that. Again, if the number was 56, you'll be left with 6 here, and it'll do the same thing. It'll subtract, here I subtract immediate, but it'll subtract 1 from 6 times. It'll hit 0 or a negative, and it'll branch down. And then 1's will contain 6. So I'll have my values split up between these two variables, the 10's place and the 1's place, and all that's left to do is to put them out onto the LEDs. Now the 1's I shift over, logical shift left twice, because the LED bits are on 2 and 5. They don't start at 0, they start at 2. So I shift them over twice and then put the 1's out to them. I do it by doing a mask, setting it all to off. 1's is LED off. Do an exclusive OR comparison. So anywhere there's a bit on in 1's, it'll make mask 0, and then it'll make 1's 0. I'm applying mask to 1's, and then I output 1's to port D, and that'll print out the 1's through the LEDs. Do the same thing with 10's. Mask exclusive OR to 10's. It'll flip the bits in the 10's, and then it'll put out that to port B, which is the 10's place. Lastly, state 4 effectively does the same thing as state 0, minus setting up the variables. It'll wait for a 1 to come in, so you block until 0. Oh, I'm sorry. This blocks until 0, so it waits for a 0 to come in, and then it jumps back up to state 0, which resets the variables. And then that waits for a 1 to come in, and then the whole thing goes through again. It just keeps going. It does this about every 10 milliseconds, every 10 or 11, because you have these extra things down here. So it's doing it, 100 times a second. It's updating the temperature. And yeah, basically, I do have a video of it working, which I will throw up now so we can see it.